let's continue our trying to the previous lecture where we were trying to arrive at a duality between two different points of view. It's a bit too loud today, no? Okay, and the two different points of view are the following. So whenever we have a physical system where we have some probe that passes through some heavier operator, we can often think of this interaction as either summing over all the ways these two objects can interact, by summing, say, Feynman diagrams, summing all the exchanges they can, everything they can exchange, or by thinking that the heavy guy generates some effective background where the light guy propagates, and if we can manage to quantitatively describe that background, that's an equally good description. So, from the point of view, and this is also very closely related to the point of view of a duality between open strings and closed strings. The same kind of diagram where you describe a closed string that becomes some open string that propagates and then emits a closed string. This is one possible story to describe this picture, right? But another story is to say, no, I had my brain, and my brain started popping out closed strings that start getting out, and then they were emitted. And that's an equally valid description. So we can have a description in terms of open strings that propagate here and go away, or a closed brain that started popping out closed strings. And both descriptions are totally valid. So if we see it from one point of view, this looks like an open string. If it looks from this point of view, this looks like a closed string going away. And the idea is to try to sum over all these interactions to some probe. The probe we did was a closed string, but I could have considered the probe where I have, for example, one single brain, and I'm scattering some single closed open string on this auxiliary brain, and then the brain will interact with my stack of brains, and then it will be an open string brain, an open string probe. Okay? So instead of putting a closed string, I could put a brain which would be a probe brain. And here we would have a huge stack of n brains. Okay? I actually printed some page of with some properly drawn picture because these pictures are kind of hard to draw. And in one of them you see how this process would look like when you would have, it's upside down, you have some open strings and then they can interact with this closed brain. Right? It's one of the pictures that you have there. And on the other side, from the point of view of an open string, you have on the other side, or I don't know how it was printed, you can imagine that you have some open string process described by a fat line notation. Okay? Very good. So, again, back to this example. So, we were saying that we have some probe that propagates. And we can think of this propagation, we can think of these holes here on the worldsheet of this closed string as inserting some closed strings. Okay, we can think that we have some Riemann surface, and we cut the Riemann surface along some circles where we put some state, which is a closed string state. Okay? But then we know that we can also describe it, instead of putting a state, putting an operator. So instead of putting a state here, I can continue it down and insert an operator. And summing over all these operators inserted in the worldsheet of a closed string is the same as saying that I deform the background where the closed string moves. And again, it's important that the background is heavy, otherwise it cannot deform the background. So we have some effective background, and this is the relation between two descriptions, A and B. Now, A is kind of simple. A is like, you can really imagine that this stack of brains is like our table, and we have some experiment on our table, which it's not a superconductor, it's n equals 4 super n mu's. And this theory, of course, it lives in 10 dimensions, there's also gravity and so on outside, but at low energies we don't care about gravity, we only care about our table and the experiment in our table, and that is described by n equals 4 super n mu's. Okay, plus the gravity that was decoupled. Can be there as well. Okay, very good. So again, this point of view that, for example, from the closed graph point of view, you see that you have loops in your graph where the index is always the same, it's always the same index k, which you can interpret as an if you want, you can interpret, again, it's just our interpretation, as an interaction with the brain. And the fact that a string has always the same index k there means that it's a string that's touching a brain and landed on a single brain. So the fact that when you cut a string, you have some closed string that came from brain number k. So here I can imagine that there is a string coming out from this hole, from this loop there of color, which is a closed string. And I think the cartoon that I would draw for that picture, if I'm not mistaken, will be something like this, which if I want to draw on the plane, I consider my two operators to be here and here. This is some funny notation I'm using for a single trace. I'm opening it up to look more like a cylinder. And I will start drawing some Feynman diagram. I can draw it on the cylinder like this, or on the sphere like this. And this, you see described, looks very much like a propagation of a closed string. Non-trivial closed string, non-trivial vibration. A priori, I don't know where is the space-time where this string is living. It could be some non-trivial background. Right? A priori, who knows what the effective theory for that complicated mess there is. It's some complicated background. But again, I can think as these loops here, as saying that I have some closed string that is moving and interacting with the brain. This was when the string touched the brain. This is one thing like this. And I can think of this picture, can interpret also these loops of color as interactions with some brains of some trivial string. So there is a trivial string, and it looks complicated because it's interacting a lot with the brain. Okay, very good. Okay, so these pictures, they are not exactly the pictures I gave you. You might be a bit confused by some of the words because they were taken from, they were not prepared explicitly for the lecture. I just thought it would be nice to print them 10 minutes ago, so I didn't have time to properly tailor them, but I think they more or less capture the spirit of what we are discussing. Okay, very good. So now we go to side B. We go to ask ourselves, okay, what kind of background? Yes.
Maybe a small question. So this n equal to 4 super numbers you get from Nambu-Goto action for the brain, or?
Okay. So again, so how did we describe effective actions in string theory? One way of doing it would be to start with the brain, study open strings, see how they scatter, compute a scattering process of 4 open strings, and then see how the massless modes on the brain. The massless modes. Okay, maybe it is a good point. It's important to emphasize that the massless modes, we have some index I to tell which brain this endpoint is, and index J, and you have these massless modes, A, mu, I, J if you want. There's also other modes, but in particular there are these massless modes. Okay? These are contained there. And then you can ask, how do these massless modes scatter? You study a scattering amplitude in string theory of these massless modes, and you see that they scatter in exactly the same way as you would predict from n equals 4 super unit, from the scattering in a gauge theory. And then you could repeat the same exercise for all the massless excitations, and in this way reconstruct the action. Another way, you can start with the effective action for the brain with Born-Feld, and expand it, and then indeed you would get to n equals 4 super unit. But it is my guess that probably people did not discuss Born-Feld, so I would rather not mention those words. Is it true? Very good. I also noticed that yesterday I tried to start from the so-called Polyakov action, but then I was told that you actually never saw the Polyakov action. So the starting point that was there in the corner, and I said string theory is sum over CFTs, and I wrote some action, you should have complained. That action was probably not very familiar for you, right? You had seen something called the Nambu-Goto action, where the action of the string is the area of the string. And I wrote something that looked a bit different, and it can be shown that the two are equivalent. So I don't know if, did you receive an email with some recommendation of some pages that you could check to see that both are equivalent? You can introduce some metric on the string, integrate a metric out, and you go to Nambu-Goto. Okay. Is it okay? So it's like saying, for example, when you do first quantize one particle, you compute what's the propagation from a particle from a point to the other. You can write a sum over paths, exponential of the length of the path. But you can also describe it with a Lagrangian, which is x dot square plus m square x squared, which doesn't look like a square root at all. And the same kind of tricks, you introduce some field bind, some metric, and when you eliminate that metric, you go back to the square root one that you started with. Okay, so it's very much really in spirit. So please have a look if you have not seen Polyakov action. Please have a look at the pages that are recommended, or at the first chapter of Green-Schwarz-Schmidt at the very, very beginning. He discusses this analogy with the particle, and it might be useful for you, even though we are not going to use it until probably Monday. But please have a look. Okay. So now we ask ourselves, what background do these brains generate? Okay. So what's the background B? What background do they generate? because you ask yourself, what's the low energy, how do I describe what background a heavy object creates? Okay? If it's a point-like object, it is just some black hole. Okay? Now, you have a theory of a spherical object, it will be a black hole. Now, you have an effective action that tells you that that string theory contains gravity plus other stuff, right? So you have some equations that tell you that R mu nu is equal to T mu nu, and you have Einstein equations, G mu nu is equal to T mu nu, you have Einstein equations for coupled to some other fields in this 10-dimensional supergravity low energy description. Okay? So whenever you have some very heavy object, very heavy, like a stack of n branes, it's a hugely heavy object, you can ask yourself, okay, let me go to this effective action, let me go to these equations of motion for my metric, for my background field, and as a source, let me put some very heavy plane. Okay? And let's see what solutions to these equations I get. Yes?
Sorry, quick question. So when you stack your branes, do they have any separation, or are they infinitesimally separated?
No, they have no separation. That's important. If they had a separation, then a string that stretches between I and j would be massive, because it will be stretched. Okay? So there is a tension, so something that is stretched has some mass. Okay? So it's important that this branes, a stack of n branes, is some brane, they are all at the same position. So here, for example, I separated the brane a bit, and okay, and that's it. I don't. It will be a bit of a detour to discuss. So you can discuss massive strings if you separate branes. Then you can have some scattering of massive objects and so on. You can do it. And if you want, you can ask me at the end how you would. Okay. So then, just by looking for some solution of the equations of motion for the effective action in the presence of a very heavy object, you can find how the background looks like. Okay? So let me write a solution and a few comments. Okay? Okay. So the background, okay, so the effect of putting some heavy object, which is a plane, okay, from this heavy plane is the following. So you have eta mu nu. Let's write the solution and then it will become, I hope, dx mu divided by square root 1 plus L squared L to the 4 over R to the 4 plus square root 1 plus L to the 4 over R to the 4 dxm dxm. Okay? Where m and run from 4 up to 9, mu and nu run from 0 up to 3. Okay? And R is xm xm. So what we have is an ansatz where we have some brane, okay, which contains the directions x mu. So it contains the time direction and 3 spatial directions. So it's a D3 object. It's a 3 plus 1 dimensional object. Okay. And then we have the orthogonal directions xm, and the metric should depend on the distance from a point in the bulk to the brane, which is the distance I. Okay? Is it okay? So this would be the most natural ansatz that you would write. A priori, you would put here some function g of r. You would put here some function f of r. You would plug into the effective equations of motion, okay, effective, modified GR equations of motion, and you would find F and G. Just find what background does a heavy source generate. Okay? Very good. And you can relate L to the parameters that we are working on by the formula L to the 4 equal G string N 4 pi alpha prime squared. Okay? So the brains, they let me just tell you that you can find it. Okay, any question here? So this again is done by putting this stack of brains. You know how to identify how many brains you are putting because you can measure what flux they produce. This object, they are charged, and you can, as you know, and you can measure, you can identify the mass and the charge of these brains and make sure you are putting the right object in this effective description. You make an ansatz for how the background should look like. You plug it into this generalized Einstein equation and you see what does a very heavy plane generate. And they generate a solution that is called the black brain. It's not a black hole, it's called a black brain. Okay. A black 3 brain. Okay. Okay, very good. Okay, so let me see. What else do I want to say? I think this is probably it.
So is this a vacuum solution outside of the brain, or you put some T-mu on the right-hand side?
No, it's vacuum outside.
It's vacuum.
Yeah.
And so, where does the L come from?
Sorry?
Where does the L come from? Because
from the source. So there's a source, a delta, that will be proportional. The source that you put at this R equals 0 will be proportional. The strength of the source will be proportional to the how many brains you put.
So you put delta like source.
Yes, you will put a localized source, and that localized source, the strength of that localized force, how strongly, how heavy this object is, would be dependent on this L. Okay? In the same way that if you put some cosmic string or even some particle, you put some localized source that is proportional to the mass of your particle, or to the mass, or to the density of your cosmic string. Same thing. Okay, very good. Again, of course, it would be a bit, I mean, one could do it. It would be possible to just write effective action, study the solutions, and so on. It's an interesting thing to do. Maybe it's a good thing to do to prepare for a homework. Maybe I'll try to prepare a homework where you can get this solution from the effective actions by plugging them into the equations of motion and so on. But I don't know. I have to see if it's too technical. People are complaining my homeworks are too technical. I'll see. Okay, very good. So, any question here? Okay, so L sets a curvature scale. L sets the scale of a curvature. And the gravity description is best if L is large. Okay. So we have a good gravity description if our space-time changes at scales which are much bigger than the string length. Otherwise, string effects are important. So if the space-time changes at scales which are much greater than the string length, then gravity is a good description. So this is a good description. It's a most useful description. Okay, for L much bigger than the string length, which is equivalent to G string times N, which I remind you was what we defined as the 't Hooft coupling, much bigger than 1. While, I remind you, the description A was most useful at weak coupling in the gauge theory when it's very simple to do computation. So it was most useful for lambda much smaller than 1. Okay? So this already hints to one of the great remarkable features, but also challenges of this duality, is that the duality will relate two descriptions, and one will be very easy to compute when lambda is very small, and the other is very easy to compute with lambda is very large. So it's extremely powerful because it maps what we don't know how to compute in one theory to what we know very easily how to compute in the other theory. But it also makes it a challenge because we have a duality and then it's a pain to check anything because, okay, you can compute something at very weak coupling there, but that will describe super strongly coupled things here and it will be a pain to compare. So it makes it very hard to test, it makes it very challenging to test, but very powerful at the same time because it gives us a description that is useful in totally different regimes. So now let's extract the physics. Now some more interesting part comes of extracting the physics out of this background. So this is some background. Okay, well, let's see. Let's extract some physics out of it. So this is the fun part. Okay. So I want manual. So now let's extract then some physics out of this background. And let's study what happens when we approach, when we are very close to the brain or when we are very separated from the brain, right? It's the most natural thing to ask. So what happens if you go very far away from the brain, okay? So if R is much bigger than L, what do you think should happen? Even before looking at the solution. You are very far away from the brain, you see flat space. Of course, you do nothing, right? You put an heavy object, then you go to the 50 light years away, of course you see nothing. And indeed, when R is very big, all the square roots just become 1, so the metric ds squared goes to just eta mu nu dx nu plus, okay, the other directions are Euclidean, so delta mn dxn, which is just the 10-dimensional flat space. Okay, very good. So this is the 10-dimensional flat space. It's Minkowski, 10-dimensional Minkowski space. So this guy is nothing but minus dt squared plus dx1 squared plus dx2 squared plus dx3 squared. Okay? So a comment I want to make is that t here, delta t, if you compute something and tell me delta t equals something, okay? You know very well that telling me something like some coordinates is separated with some coordinates is some number, a priori must be very careful before attaching some physical meaning to it, right? Coordinates are coordinates. So what you attach a physical meaning is to the line element that tells the proper length measured by some observer. So if you put an observer at very large distances, then, and fixed, then all the dx's are 0, so dt is identified with a proper time for an observer at infinity. Okay? So delta t is the time lapse measured by someone at infinity. Okay, very good. So delta t, which we also sometimes call, you see, because these dx mu are the directions inside the brain, sometimes we call this t the brain time. Okay? For obvious reasons, because this dx mu, they describe Minkowski space on the brain. So this t brain, just be careful what we mean by this t brain, is the time measured by an observer at infinity. Okay? Very good. What about when we are very close to the brain? Now it's the other point. Now let's go very close to the brain. And this was the key insight of Maldacena. So no one before had tried to study what happens in this language. Now studying what happens very close to the brain and seeing if there's something interesting going on. Okay. So what happens now close to the brain? Sorry, yeah, close to the brain. Well, close to the brain, so we have now if R is much smaller than this L, this dimensionful quantity built out of the only parameters we have, then the metric ds squared becomes, what does it become? It becomes the following. Let me write it in the following way. It becomes R squared over L squared, then that square root becomes very large, and you can drop the 1. And dropping the 1 is really the key insight, because as soon as you drop the 1, you will recognize we recognize a very special space-time that describes the near horizon or the near brain limit. And we get eta mu nu dx mu plus L squared over R squared dxm, which you can write in the following way. You can write this guy in spherical coordinates as dr squared plus r squared d omega of a sphere, 5 sphere. Okay? So you can write this 6 dimensions as in radial coordinates, just like we did several times in the beginning. And then what we get is r squared over L squared. Let me just rewrite and put some brackets. Dx mu. So I'm just rewriting again, moving the indices up and down for some strange reason. I don't know why. And then L squared over R squared dr squared, and we put some bracket here. Now this is some 5-dimensional space plus a space that, okay, that one we know very well, is a sphere. So this is just a 5-sphere. And this metric here is nothing but the metric of AdS5 spacetime. Okay? And since you already studied it in one of the tutorials, let me just tell you that to recognize it in the form that we have seen before, you do the change of variable z equal L over R. Okay? To recognize it in Poincare variables that we have used before. But for now, let's not worry about that. This is just later if you want to make contact with what you have seen in the first tutorial or second, you can do this change about. This is nothing but AdS5. Okay, very good. So what we are getting is that close to the brain, okay, so the near brain, which is called the near horizon because r equal to 0 can be thought as the horizon as this brain, so it's at 0, so there's effectively nothing inside, but so the near horizon or the near brain geometry is AdS5 times S5. Very good. But okay, now I have some space-time and I have AdS5 times S5 close to the brain. And I have flat space far away from the brain. And here I have gravity far away from the brain and then equals 4 close to the brain. So we are almost tempted to say that this guy should be dual to strings in AdS5 times S5. But we need to be a bit more careful, understanding how could we be so bold to reach such a conclusion. So let's continue exploring the physics and see what is the time measured by an observer that is close to the brain. So the time measured by someone close to the brain, okay, so delta t measured by someone close to the brain, is just r over L times delta T brain, which is delta T measured by someone at infinity. So we have this redshift effect that times are very different. The times measured by someone close to the brain or far away, they are very different, and they have this overall effect. Again, this is just ds. Both of them are just ds, the proper time. Is it okay? And in particular for energies, we get, of course, the opposite. So the energy for someone close is equal to L over R times energies for an observer at infinity. So then, this huge, let's see what's the effect of this huge red blue shift. Let's see what happens. So suppose we start, this is infinity, so we are very far away from the brain, so the brain is there, and I'm here. Okay, so someone is here. Yeah? It's okay? And there's someone else here. Okay? And this someone else has something, can be some string, there's something that has some energy. E. Some proper energy. An energy measured by him. We both agree what it is. A piece of plutonium. It's okay? And now, this guy decides to move close to the brain. Where we have AdS5 times S5 geometry. Now, what will happen is that for me, from my point of view, from the point of view of this guy, as he's moving, his energy is becoming thinner. I'm seeing it as becoming dimmer and dimmer, this flash of light that he has. Now, for him, it's his proper energy. I mean, he just walks with this piece of plutonium. It's always radioactive. It's not very wise, but okay, it's always the same. It doesn't change. But for me, that I'm at infinity, I'm seeing it becoming more and more red, to the point that when I am at infinity, when he is close to the brain, whatever was originally, now it looks like something with very low energy. Independent of what we started. This is always from the point of view of someone at infinity. Okay? From the point of view of someone walking with a piece of material, some radio or whatever, it's always the same. So we conclude that for someone at infinity, there are two things, but like a better word, that have low energy. Okay? So they are, what has low energy for me at infinity? Well, we have supergravity, the low energy, the gravitons and so on, in what's called the bulk. Okay, this is in the 10-dimensional flat space. Okay, so I'm here at infinity. When I see flat space and I see a bunch of massless modes moving here, that's definitely some dynamics at low energy, right? It's just the same as in empty space. Plus, and now the important is anything close to the brain. Anything close to that brain, from the point of view of someone at infinity, is a low energy because of this huge redshift. So by anything, we mean really, for example, any strings. Massless, massive, whatever. Some massive strings, from the point of view of someone at infinity, they are also low energy modes. So the low energy modes, seen for someone at infinity, is not just the massless modes at infinity, but rather anything that is approaching this horizon. Yes, the full quantum theory, the full quantum gravity theory close to the horizon is, from the point of view of the guy at infinity, a low energy effect. And for the usual kind of reasons, if you have gravity and if you have some other system, at low energies gravity decouples exactly the same way as here. Okay? You can also do some gravity computation to show that it decouples by computing what is the absorption cross-section of gravitons to the brain and see that the brain is very bad at absorbing gravitons, so it interacts very weakly with it. But the usual intuition is still correct. Gravity will not interact, will be free at low energies. So we conclude that point of view B tells me that at low energies, we have a description in terms of full string theory. Okay, let me emphasize. Full string theory in this near horizon geometry, AdS5 times S5, plus supergravity in 10-dimensional Minkowski space. Okay? Another way of seeing that when something is close to AdS, it will not couple much with something outside is to realize that AdS is a gravitational box. It actually protects what's inside. And this you played a bit in your exercise, in second exercise, right? Seeing that AdS can be understood as this gravitational box. But we will see this in some more detail later. At the end of the day, what we conclude is that we have two equivalent descriptions. One, and both of them describe something plus decoupled gravity, so we can just cross it over. And we conclude that strings in AdS5 times S5, or super strings in AdS5 times S5, should be an equivalent description of a very precise gauge theory, which is n equals 4 super Young-Mills in 10 dimensions. And this is what is called the AdS CFT duality. Okay. Any question? Yes. Sorry, yes.
On that blackboard is 4 dimensions supergravity.
No, 10-dimensional supergravity.
I mean,
In this blackboard, we have the brains, which is our table. The table is just in 4 dimensions in our 10-dimensional space, and open strings that move outside the table in the full 10 dimensions. So it is a 4-dimensional n equals 4 plus a 10-dimensional gravity. Here, close to the geometry, we still get some 10-dimensional metric. It is a 10-dimensional theory, which is AdS5 times S5. And that 10-dimensional theory is dual to a theory in 4. No, here, of course, 4D. You meant here. No, here, of course. Sorry. No, of course, it's a typo. So you have a duality between, where is blue chalk? Okay. We have a problem. Very good. Okay. So we have a remarkable duality between a string theory in 10 dimensions and a gauge theory in 4 dimensions. Yes.
So maybe a related question to that. So it seems that actually on the right-hand side you are talking about the observer at infinity, which is very, very far from the brain, whereas on the left-hand side you are talking the n equal to 4 or less on the brain. So if I'm off the brain, I don't see it, right? So you should be comparing the observer.
No, I can say the same thing. So I'm here, and the brain is there, and I have 2 descriptions at low energy. One description is to say, okay, someone is doing experiments there, that's n equals 4 supreme wheels, and there's gravity here. It's the same. Another description is to say, no, this is a geometry, and here I am in flat space with gravity, and there is a deformed geometry. So I can phrase it always from the point of view of someone standing far away from the brain and asking, what is the low energy dynamics? And it's always whatever is in the brain plus whatever is close to me that I'm infinity, which is 10-dimensional supergravity.
So both point of views are from the for the distant observer, you are saying?
Let's say it that way. And these arguments that they decouple, you see now this justifies the name of all this chain of arguments. This is why it's called the decoupling argument. It's the notion that we have this description from the observer at infinity, and this 10-dimensional gravity decouples for whatever you do at the brain. And from one point of view, what you have is open strings described by n equals 4 supreme wheels. And from the other point of view, what you have is anything that goes there because of the huge redshift. For me, it's a low energy thing. Okay? Okay, very good. You can work out more carefully the mapping of parameters. So L is called the radius of AdS. But before writing down what's the mapping of parameters, let me just emphasize that, to have some duality between the 10-dimensional theory of quantum gravity. See what I mean? It's really something very, very powerful what we are claiming. We are claiming that we have a theory, which is the 10-dimensional theory of quantum gravity, being dual to a 4-dimensional vanilla conformal field theory. It's really something, a priori, it looks so insane that there are actually there's a nice review article by Joe Polchinski, where he starts a motivation, and at the end of the introduction he says, find some arguments for why it is obvious that a 4-dimensional theory, 4-dimensional conformal field theory can never be dual to a 10-dimensional string theory. Because a priori, it looks so crazy that you could imagine finding many, many such arguments. And then the second question is, show that your arguments are wrong. Because they have to be. Because we do have such crazy claims. Okay, very good. So, let me just discuss a bit how do we map the parameters between one theory and the other. So you see that, for example, the metric so the relation between, so you can write the action of the string as square root lambda over 2 pi integral of this g mu nu metric dx mu dx mu. And you can make all these dimensionless using L. Okay, you just redefine your coordinates to be dimensionless using L. For example, you do something like this, z equal L over r, then r is always measured in units of L. Then, what was here before was a string tension, now it's redefined, it must always be dimensionless because the action is dimensional. So what we have here will be, if you do this exercise, L to the 4 over alpha prime squared. Just L squared over alpha prime, of course. So the map, or proportional to, so the map is that lambda, what we write here, is identified as L to the 4 over alpha prime squared. And this lambda is, this is on the string theory side. And this lambda is equal to G string times n on the gauge theory side. Okay, so if you work out the parameters where alpha prime is, L you see contains some G string and some n. So if you work out carefully, if you divide one by the other, and there are some pi's that I'm probably forgetting, but okay, maybe there are some pi's here, I don't know. But you see easily that that quantity indeed is nothing but G string n. n in Young-Mills is the number of colors, and G string, which sorry, let me write. And G Young-Mills square is equal to L to the 4 pi alpha prime square 1 over n. So this is just lambda, so clearly I'm missing some factors of pi. And this is nothing but G Young-Mills square. So it is what we pay whenever we have an extra loop in our Feynman diagram. So we have this G Young-Mills square whenever we have a hole. Sorry. But this is nothing but G string. That's what I want to say. So you have this mapping of parameters. So let me summarize the important one. What's important is that lambda, which is the tooth coupling, is related to L. And G Young-Mills square is just as we saw already way before, the G string. So this is all you need. Okay? So notice that this is a map between just dimensionless quantities. And this is exactly what ought to be. So these are all dimensionless. And this is crucial because, I mean, remember that we are describing a theory, a conformal field theory that has no scale in terms of a theory of AdS. So, of course, AdS has a radius. So how could it be that we have a duality between a theory without a scale and a theory that has a radius? No, that's okay because we have a radius. But what we can say is that we have a parameter which is what is the radius of antecedent in units of string length. Okay. What is the radius of the antecedent in units of string length? That's a dimensionless parameter. And that parameter is related to the coupling of my gauge theory, which is another dimensionless parameter. Okay? So the way to think about it is that there are two ways of thinking about it. I mean, the correct way is always to think only in terms of dimensionless quantities, but we cannot help thinking in terms of dimension for some time. So let me do it still. Suppose, how can I think about it? I can think that if I say that I have my string, it's fixed, it's a string of a given material, someone gave me a string, it has some tension. Okay? And then I have some theory, some gauge theory, some parameter lambda. And I can tune this parameter lambda from weak to strong coupling. And the claim is that I will be describing a dual theory of quantum gravity where the radius of AdS is either very big or very large. Then what will change is the radius. So lambda going to infinity, we describe a theory dual to AdS with a very large radius, which means that the curvature is very small. It's weakly coupled AdS, when AdS is very simple. When lambda is very small, it describes a theory where the AdS radius is comparable to the string length, but then the quantum effects from the string become very important, like when you try to put a particle in a very small box. Then it becomes crazy, hitting the walls like crazy, right? Okay, very good. So let's see. So let me summarize what do we have and what should we do. What do we need? So next. So what's next? Oh, very important is to say that two theories are dual to each other is kind of useless. So we need a dictionary. We already have some dictionary that tells us at least what parameters correspond on each side. But we need some kind of dictionary. Right? I mean, we need to know if I compute, say, anomalous dimensions in my gauge theory, which is a conformal theory, in Young-Mills, what should I compute on the string theory, for example? Otherwise, why do I want a dual description? If I compute something on one side and I don't know what it corresponds on the other side, then it becomes a bit useless. So we definitely need a dictionary. Something that we should also do is the next natural step would be we would like to have evidence. That is, checks of the duality. And then another point we want to do is that we want to understand a bit more the geometry, more on the geometry of AdS. Okay. Oh, not much, because you already explored it thoroughly in one of the tutorials, but I would also like to discuss a bit more the geometry of this anti-receipt of space-time. And then, maybe in a slightly different order, probably this is where we are going to start, we should provide some more intuition, that is, more intuition for the duality. Okay, so they are in a bit of a strange order. Probably this point will actually be the first one. Right? So I promised you that I will give you a couple of hand-waving arguments for the existence of this kind of duality. So we started with large N. Then we went to the so-called decoupling argument. But now there are many, many comments we could do about this duality. And for most of tomorrow's lecture, that's what I will be doing, providing some comments about why is this duality plausible, and some further hints that this is something that we could expect. So for now, let me just emphasize the feature of the duality, which is that lambda much smaller than 1 is easy for the super Yang-Mills theory. And this corresponds to what? Corresponds to string whose tension is very small. Right? String whose tension is very small. So it corresponds to very quantum strings that wobble like crazy. Very, very quantum strings. The tension is not suppressing at all their vibrations. It's really an insane regime. So it's very hard. And lambda much bigger than 1, it's very hard for Yang-Mills, because you are asking, it's very hard in super Yang-Mills. I mean, you have some theory, you have some coupling, and now you ask what happens at strong coupling. I mean, what can you do? Monte Carlos, I mean, it's very hard to have perturbative, to have analytic tools. But this is dual in as long as two classical strings, where because the tension is very big, the string just moves along some string equations of motion, whatever follows from the action. Because the tension is very big, so the path integral over strings is just dominated by the classical solution. And then there is n. So n, much bigger than 1, okay, means planar graphs here. Okay, planar graphs makes our life easy. And on the string theory, n much greater than 1 means, okay, if you keep lambda fixed is equivalent to saying that G string is much smaller than 1, means free strings, strings that don't split. This is a handle, there's no handles, and this is also easier than usual strings. So, from the point of view of the duality, there is indeed one limit where both theories simplify, which is the large N limit, where we get planar graphs only, and on the other side we get free strings. But then, from the point of view of lambda, the situation is quite different. There is the easy regime of one theory is mapped to the hard regime of the other theory, and vice versa. And that is one of the powers and also challenges of AdS CFT. Which is that even if you say that I'm only working in the planar limit of the gauge theory, and I'm only working for free strings, it is still quite a challenge to check this duality. But it also makes it very powerful, and nowadays this duality is understood as one of the very powerful tools for studying strongly coupled systems. Because strongly coupled systems are systems for which it's normally very hard to control. But through the duality, it becomes a very simple problem. So, but again, this will be part of the comments that I'll be making tomorrow. So, I think okay. So tomorrow we will try to make a few comments more about the duality, and I will try to answer this question about the dictionary and give you this example. What does the energy, the dimensions in n equals 4 super n meals correspond? Very good. Questions? Yes.
So, is there such a mapping for every CFT and for the order for specific CFT?
Oh, that's an excellent question. Okay, but maybe that's a perfect question for tomorrow. So let me say that, okay, let's try to think just a bit without too much detail. So what was, for example, imagine you have a CFT where you have no notion of large n. So your fields are not large n matrices. There's no notion, for example, of large n factorization, right? So if you have correlation function of 4 operators, they are not dominated by just a disconnected piece plus some connected part, right? Then immediately your interpretation in terms of strings becomes quite tough. That is, you might have a dual description in terms of strings, but then that must be very interacting strings, right? I mean, then if you have a theory that is described by very interacting strings, okay, is it still useful to have a dual? Right? So immediately we see that it's very important to have some way of having some large n factorization, some notion that when you have correlation function of operators, they like to decouple. That corresponds to the intuition that to leading order strings like to propagate freely, and only to subleading order they interact. Right? Then, for example, this is one of the conditions. So CFTs, if you want to have a useful ideal CFT description, they ought to have some very large n. But there's more, for example. You can, okay, but there's more, and maybe tomorrow it will be a good point to discuss. But the answer is, by no means. I mean, a priori, it is very hard to establish a precise correspondence. This is a very precise example. I can write Lagrangians and actions on both sides. But normally, it's quite a challenge to do so. But there is one constructive way of proceeding. For example, you can start with your favorite brain setup. Instead of putting the 3 brains, you can put some other brains. Study the solution that you get from gravity, study what's the effective description on the brains. And people do it. So there is a very vast number of very precise dualities that once you have them, you can forget about these hand-waving decoupling arguments. But where the decoupling arguments are extremely powerful. You just decide to put some brains, you solve the equations on the presence of those defects on gravity, and you start generating this effective description. So there are other examples, other precise examples of the duality. But if you ask, is there a gravity dual of some 3D Ising model, for example? Well, a priori, the 3D Ising model does not exhibit some factorization, so I cannot imagine that there should be a useful gravity dual for the theory that describes phase transitions in water. I mean, there might be one, but it might be a very quantum string theory. Yes?
There were some people here in cosmology who are studying de Sitter, CFT, correspondence.
Yes.
Is there much known about that field?
No, very little. It's a very interesting problem. People are indeed trying to understand what could correspond to studying a duality between de Sitter and anti-de Sitter. So the physics of anti-de Sitter, as I said, is a gravitational box. You have a box, it's a cylinder filled with something inside, and particles, if you throw a particle inside a cylinder, they go, they come back, they stay inside the cylinder. It's really a box. The physics of anti-de Sitter is different. Anti-de Sitter describes an expanding universe, and it's a challenge to think about the duality between de Sitter and anti-de Sitter. But there is lots of progress and lots of conjectures made, but there is not an agreed point of view. Now, for example, one point of view is that actually, if you look at the metric of de Sitter and anti-de Sitter, they are just related by some minus sign. So you can just imagine trying, can I get from one to the other by an analytic continuation? Can I start with AdS CFT, start doing an analytic continuation of my parameters, and go to the ES CFT? Okay, then you look and you ask, okay, so what is the analytic continuation I have to do at the level of my CFT, say? So I have a CFT which has n collars and coupling G and mil. And you can ask, can it be that G and mil goes to minus G and mil or something like this? That would be okay. But, and I hope I'm not mistaken, if I remember correctly, the duality, actually, if you follow the duality, you have to send n, the number of colors, to in, where I is the complex square root of -1. So it's kind of a tricky limit to do. Of course, if you could control it exactly, the theory, maybe you could imagine doing so. I forgot if it was in or -n, but in any case, it was something that clearly was very incompatible with n being a number of colors. But still, there are theories that you can do it. And for example, there are some theories where you can understand what does the analytic attenuation do, and you can show that you go from some ON theories to some SPM theories. And there is lots of interest in trying to understand this duality. It's a very important question for quantum cosmology. And very, very little is known about AdS CFT, and it's very interesting. Yes?
So maybe this can be made really precise, and it's a sort of a proof of this. What you showed us, it's a proof of this?
Yeah, I mean, it almost looks like a proof, right?
Yeah.
So, but, okay, yeah, I don't know. Some people would roughly call it a proof, some people would call it a conjecture. I think it's not a proof. I mean, I don't think it's a proof. You have many things, this decouples from this. And I feel like I hand-waved well a bit. I mean, I can still sleep well, but I wouldn't call it a proof. My standards for proof are a bit higher. I think no one would call it a proof. Yeah, there is some assumption that you can take this weak coupling limit and that there are no non-perturbative effects that could appear. I mean, there could be all sorts of fun things happening. So I will take this as almost a proof. And then with a few more checks that are highly unlikely, I would say, okay, I'm satisfied now. So I think this, together with a few checks that are really non-trivial, I mean, not based on symmetries, but I think that would satisfy. And those checks exist, so I mean, I have no doubt that this duality is correct, of course. And no one has. More? Okay, very good. So the hard part is done. Now we will go back to a bit less hand waving.